What is the Higgs boson? I'm sure you've heard of it. A particle which should complete the standard model of physics and give an explanation for the origin of mass and hopefully the nature of gravity as well. Now you may be thinking, we already know about that. Newton already explained gravity and mass. Well, yes, but actually no. We don't understand either yet at a fundamental level. Now I mentioned the standard model. But what is that? Well, it describes the universe as fermions, which are matter particles, and bosons, which are force-carrying particles. And this distinction is important for the following reason. If I want something to happen, say I want this coffee cup to move, I have to exert force, and so I push it with my hand. My hand is the vehicle for this exchange of energy. But theorists determined that forces that act at a distance, like gravity and magnetism, also require some physical interaction to direct energy. Otherwise, the energy doesn't know where to go. Energy doesn't know things. So the idea of the boson, a particle which could carry energy over these immense distances, was born. But while we were able to find bosons describing every other distance force, gravity still eluded us because, well, frankly, we still didn't understand mass. We've always assumed mass was an intrinsic property of a particle, but we have no idea where it comes from or why different particles have such wildly different masses. And so Peter Higgs developed the idea of the Higgs boson. Now, most bosons are simply messengers sent out over large distances carrying energy. They apply force via their interaction with other particles, but the Higgs boson is different. It acts through what is known as a quantum field. What is a quantum field? Well, if we know every particle has a field of probable locations, and we know there are millions of identical particles out there, we can divide the universe into layers of particle type. So there's a layer, or field, of probable particles A, B, C. All particles in the standard model are like this. Where there are particles and objects, we have higher probabilities in the respective quantum fields, and in a vacuum, probabilities are practically zero. But an object's mass doesn't change if it is or isn't in a vacuum, so Peter Higgs figured that if the Higgs quantum field was to define mass, then it would have to have a low but consistent value everywhere in the universe. But how does the Higgs define mass? Now, the Higgs's mechanism for mass is called the weak hypercharge. The weak hypercharge is constantly traded around in the Higgs field, interacting with particles that pass by at varying strengths, and this does very little to a particle with constant velocity. But once a particle tries to accelerate or decelerate from an added force, the weak hypercharge provides a counter to that force, reducing the acceleration. And let's pause with that and think back to Newton's second law, F equals ma. This is just a descriptor of how more mass causes more resistance to acceleration. And that's exactly what the Higgs field does! To recap, the Higgs boson is a force-carrying particle postulated to explain mass and gravity. Unlike most other bosons that act directly, the Higgs boson acts through a quantum field. By trading the weak hypercharge, the Higgs boson provides a resistive force that defines mass. But what about gravity? Well, while we're fairly sure that Higgs is responsible for conveying gravitational force, we don't yet know how, but once we do, I expect it'll usher in a whole new era of physics. Thank you for watching.